We are given a periodic function f of t equals t squared minus t, defined on the interval from minus pi to pi, with period 2 pi. Our goal is to obtain the full Fourier series expansion of this function. The full Fourier series on minus pi to pi is written as a 0 over 2 plus the sum of an cosine n t plus bn sine nt. The coefficient of 0 is 1 over pi times the integral of f of t from minus pi to pi. An is 1 over pi times the integral of f of t cosine nt dt. Bn is 1 over pi times the integral of f of t sine nt dt. First, we calculate a 0. Substitute f of t equals t squared minus t. Integrate term by term to get t cubed over 3 minus t squared over 2. Now evaluate from minus pi to pi. Notice that the t squared terms cancel, and we are left with 2t cubed terms. Therefore a 0 equals 2 pi squared over 3. Next we find an. We split the integral into two parts, where I1 is the integral of t squared cosine nt, and I2 is the integral of t cosine nt. We will evaluate both using integration by parts with the LIATE rule. According to LIATE, we choose U from left to right. Algebraic functions come before trigonometric ones. Recall the integration by parts formula. Integral of u dv equals uv minus the integral of v du. For I1, using LIATE, we pick the algebraic function t squared as u. So u equals t squared, and dv equals cosine of nt dt. Then du is 2t dt, and v is 1 over n sine nt. Apply the formula. The boundary term vanishes because sine of n pi and sine of minus n pi are both 0. We now need another integration by parts on this new integral. Call this new integral j again. Apply LIATE. Algebraic t comes before sine. U equals t dv equals sine nt dt. Then du is dt, and v is minus 1 over n cosine nt. Evaluate the boundary term carefully. Since cosine of n pi equals minus 1 to the n, we obtain j equals minus 2 pi times minus 1 to the n over n. Therefore I1 equals 4 pi times minus 1 to the n over n squared. Now for I2. Using LIATE again, choose the algebraic function t as u. U equals t dv equals cosine nt dt. Then du is dt, and v is 1 over n sine nt. The boundary term is 0. And the remaining integral of sine is also 0 over a full number of periods. Thus I2 equals 0. Putting everything together. Therefore an equals 4 times minus 1 to the power n, divided by n squared. Now we calculate Bn. Again we split into two integrals, where k1 is the integral of t squared sine nt, and k2 is the integral of t sine nt. We apply integration by parts with LIATE to both. For k1, LIATE tells us to choose the algebraic t squared as u. U equals t squared, dv equals sine nt dt. Then du is 2t dt, and v is minus 1 over n cosine nt. Evaluate the boundary term. Cosine of n pi equals cosine of minus n pi equals minus 1 to the n. The boundary term cancels and I2 we already know is 0. So k1 equals 0. For k2 we already computed this earlier when finding I1. It is exactly the integral j. From before, k2 equals minus 2 pi times minus 1 to the n, over n. Substitute the values we obtained. Simplifying the signs. We obtain Bn equals 2 times minus 1 to the power n plus 1, divided by n. We now write the complete Fourier series by substituting the coefficients. This is the full Fourier series expansion of the given function. The series converges to the function f of t on the open interval from minus pi to pi, and to the average of the left and right limits at the endpoints.